Hi, welcome everyone to our latest Gen3 community forum. Excited by our topic today. Today we're going to discuss data submission, perspectives and solutions from different Gen3 systems. So this particular forum is an effort to do some knowledge sharing across the different Gen3 operators or people that have Gen3 systems to share how you are sort of handling or approaching data submission. I think I found that every Gen3 Commons or mesh does things a little differently, so it's really great to learn from each other. I know even among CTDS data commons, we do things differently, so there's a lot to be learned from everyone. So thanks everyone for participating. I'm Michael Fitzsimons. As you've probably all met me at these forums, but I help do outreach for CTDS for Gen3. We have kind of a tight schedule today, so I'm going to get right into it. Um, Next slide. So we have a great list of speakers from the New Zealand eScience Infrastructure, the Open Commons Consortium, the Center for Translational Data Science, Oregon Health and Science University, and the Australian Biocommons. There's a lot of speakers, so I ask all the speakers to try to stay within 15 minutes each. If you finish a little early, we may have time for one or two questions, but otherwise we'll save all the questions for the end. So thanks again, everybody, for joining. Looking forward to hearing what the speakers have to share with us today. So I think our first speakers are Natalie and Claire, and I think Natalie is going to share her screen because she's going to do a live demo.
Good morning or good afternoon. Thanks everyone for having us here. So I'll briefly introduce our Gen3 and then pass over to Nat for the exciting part in the live demo. So we're from the from NESI, but work on the Aotearoa Genomic Data Repository. So we go to the next slide, please, Nat. So just a brief overview. We'll give a little bit of a context of our repository and then focus on the submission process for us. Because we actually keep our data files outside of Gen3, we'll focus on really metadata submission and sort of our template for that and our validation, as well as in the ingest process, which we'll give Nat will give a live demo on. Thank you. So next slide, please. So very briefly, I think a few of you will have seen this before. We're a repository of taonga species, treasured species within a New Zealand context, and have sort of access control around that. So next slide, please. So our data submission process, we have sort of an initial upfront suitability assessment just to make sure the data that's coming in is sort of within the remit of the repository. We then provide researchers with a metadata spreadsheet template. We've tried to use, as shown here, we try and use sort of community standards around that template, but it's not strictly built to any single schema. We then also give them a Globus endpoint to upload their data, and that's kind of kept separate from our Gen3. When they've completed their metadata, metadata template, we will then review it and now validate it, and then ingest it, and then on their behalf, and then provide them with a DOI for publication. So I think I can probably pass over to you now, Nat. Thank you.
Thank you. Then we're going to try to do a demo, but first, quickly, I will explain. Then we have the spreadsheet, and we wanted to have a spreadsheet just because dictionary can be quite complex, and some of the field may not mean much to the researcher. Then we are translating that in the spreadsheet that you have seen just before in terms that they understand, but it means we have to do things after to make sure we get all the data and the right format for the dictionary.
sound now, or is it just me?
examples. And I think it was a good thing that we can see in the spreadsheet, if I show you briefly again, is we have an example there, and we give them, and it gives them some ideas how to fill the spreadsheet, and it makes it much easier for them. Then it was the two things there. Then, as Claire said, the files are not loaded through Gen3, but through Globus. Then it's why we have to load this metadata this way. And what we want to do is also check for this consistency of values. And for example, we didn't have a validator at the start, and we had some values with different spelling into our metadata, and it's not great for the search. Then if after I can show you that on the system, then what we wanted also is make sure, for example, if we have an instrument, Illumina is always spelled the right way with a right number of letters, and it's much easier for searching if we want to search all the analyses that have been done with that. We do quite a lot of checks also, making sure all the data is present, and I will show you that with a demo. Then mostly we have this validator is a Python script that has been written, then it's command line. You will see nothing very fancy, but it's quite effective, and I think there is a great design behind it. Then it has the spreadsheet into mind, and if we change the spreadsheet, it load the new data, but we ingest then the spreadsheet filled by the researcher. We have the HDR dictionary, he has access to it, and is building is checking around it. And there is two outputs. One will be the validator report telling us what is wrong with the spreadsheet and with the data. And the second thing, have a TSV file. And then we can ingest through the UI with this TSV file. Then we have decided on TSV because the JSON at the start, we had some problem with some of the type. I know that now it's, I think, mostly fixed. But at the time is what we decided, then the TSV file. And also it's quite good because we are all good user of Excel, then it was quite easy to just use at the same time. All right, then I'm going to try to do a small demo. First, I'm going to show you a small data set where we have some errors and show you the errors and what type of the information we get. And we can always improve it, make it easier for the researcher. Then for the moment, only us are using the validator. The researcher sends us the data, we do it. But in the long term, and you will see, we would like to give the validator to them. Then we want to improve also how we communicate with them to make sure it's understandable and clear to them. And then I will show you a small data set with no error and show you just the ingest that we are doing. And then after we have a large data set that I can quickly show what errors we are getting with that. Then, right, here it is. Then command line, as I say, this is just how we run it. Then I'm going to do this one first, and it's our first, and it's I'm going to press, oh, sorry. Then we call the validator, we tell him the project we are using, then how we are using the project is HDR plus a number, and then we are telling him after where is the research files, and then it creates a TSV and the validation report. Then you can see I have my free researcher spreadsheet here. I'm not going to open them, but if you are interested, I could. And then it creates my validator. And when it's green, is new stuff. And if I open, here it is. Hopefully you can see, and it's big enough. Then we can see that in the file, we have a node called organism. And it tells me that on the line 17 of the organism, one of the value is incorrect. We were expecting 3 value from the dictionary, and unfortunately there is a spelling mistake on 3 of them. And then after, what is happening is we see that someone enter some of the read group, which is one also of our node, but didn't link it to anything. Then all the nodes are connected together and there is no link. Then it's telling us the researcher forgot to have these samples somewhere else. And then here also another one is one of the value was given as bid-based selection, where in fact we were expecting one of these values. Then we have found that sometimes it's a little difficult. We give the values to the researcher, but they have their own. Even if we have others, they would prefer to have their own. Then it's something we, at the end of this month, Claire has been working very hard to create a new dictionary. We are going to use our tools to migrate the old dictionary data to the new dictionary data. But also in the new dictionary, we are going to be a little more open to new field and new values and allow, but also, as I said before, we still want to check the spelling, making sure we still go with the same type of lowercase, capital, and then it is quite an important one. And that is an example of validation. And then I will quickly go through another one. Sorry, I think it's that one here. Then that one should go all easy. It's a small, and you can see the first thing he show is the version of the validator, like that we know which dictionary it's using. We are introducing a spreadsheet version, and this is the validator version itself. Is passing the spreadsheet, loading the dictionary, and then from that is build the graph and check all the data against it. And then after is validating that he has the right information. Then now I should have another file created, which is that one here. And you can see no error detected. Yeah, that spreadsheet was filled properly. Then I will show you just how we ingest. And we have two systems, a test system and a production system. The production system is the one that Claire showed you in a slide previously. I'm going to use our test system for loading just because I don't want to. Then, sorry, I have to log again in my test system. And here it is. And this is our test system. It's a little slower than our production system. We don't put as much resources. And then what we do is I select here, I think it was 53 I was doing. Then I can go to my 53. You can see I have here a project, an experiment, an organism, and the only thing we do usually to load is select the upload files. Now I go to my 53 where it has been created. The validator creates the TSV, and you can see he adds a number at the start, which tells us in which order we have to load the files. Then it's quite easy. Then now I should load my samples. He loads them, and I can then just submit them. And it is, and if I refresh, we can see now the samples are loaded. And we can do that for all the TSV, but I won't bore you with that because it goes usually quite well. Then the only thing is the project. We cannot load the TSV for the project. Then from the UI is not possible. And sometimes a little of a problem, then we have to manually create them by selecting project and enter all the data ourselves here. Then it is the only one. Then we are creating a new script for loading the project through the API instead, but it would be nice if we could do it through the UI too. All right, then what I wanted to show after is loading another file for another data set. And let me do that. And it's a very large one, or for us at least. I know that it may be when we have few thousand files. And this one is studying all the lakes in New Zealand. And there are quite a lot. And we are receiving files all the time. And I want to show you, if I go to my folder 47, and if I select the metagenomes one, we are now getting around 5,000 metagenomes entries. And if I open that and try to submit, then we have a lot of 502. And this is what we are noticing with large file. Then you can see some of them will enter properly. And I don't know if you have seen quickly at the start, we have 502 service failure. And this is what we have noticed when we are loading big files through the UI, and we're getting quite a lot of errors. And the validator, one of the next step of the validator is maybe trying to cut the files in smaller chunks to make sure. But otherwise, and after, when we'll have our API loading, where we will try to do it automatically through this. Then that's it. This is the live demo, and it went not too bad. Then whew, I'm happy about that. Then quickly, I wanted just then, what I explained is you have a project we cannot load through the UI, the project node, which is a shame. Problem with large data sets where we have this error 502. We had also some issue with Excel where some of the characters were not showing properly because in Maori, we have a few special characters like macrons. And when we had macron in TSE, we have some problems, and we're still investigating, is it Excel, is it Gen3 and all of that. We have to improve the robustness of the validator, and we have done that with all the Boolean because we have still some old version of Guppy and Elasticsearch, and one of as soon as we have our new dictionary, we will update that because we need to, and it's quite an important thing. And then we need to improve our validator to support multi-link. We have now nodes connecting to more than one node, and we need to make sure all the links are checked properly, and there are still some issues. Then what we want to do is release this validator, train the researcher to start using it for the submission. Like that, we have good data, and they can maybe only send us the TSV files, which would be better. And then hopefully later on, we would like to automate the ingestion through the API now that we are working through that. And that's it. Thank you very much. And I will stop sharing.
Thank you, Nat and Claire. I think we'll have to move along since we don't have time for questions. But for those errors, I think breaking it up sounds good, but please also post in the community channel, and somebody on our team will have some suggestions, I'm sure.
Thank you.
So now we'll turn it over to the team from the Open Commons Consortium, Plamen, Makisha, and Irvi. Plamen, are you going to kick this off?
Yes, I will. Thank you, Michael. We're the Open Commons Consortium. We built and manage data commons. We run multiple data commons, from environmental data commons to liquid biopsy data commons. But today's call and what we want to provide you information about is how we tackled COVID-19. And we have a case study that we want to provide information about, of how we brought in over 7 million subjects' health data into PRC for COVID-19 research. Next slide, please. Next. So it was March 5th, 2020. This is kind of when the official closure of businesses in the United States happened, when COVID-19 hit. And the next day, OCC orchestrated a meeting to talk about, hey, there's going to be a lot of data coming in because this is a big deal. And how can we help, right? We have expertise in data commons and data meshes. So while everybody's locked behind the doors, we're all on the phones taking charge, trying to work through how we can help, at least from the knowledge that we have of using these data commons, and then also the researchers that we have around us to do data analysis. So of course, one of our biggest partner was University of Chicago, as well as we partner with a couple other IT organizations to bring in our first Chicagoland regional COVID-19 data comments. The one way we were able to do it was first, we had to forge agreements, and that required to create common legal agreements with the regional healthcare organizations. So then ultimately we have a compliance and legal path forward to start bringing data into the environment. And then once we were able to do that, where we created commonality and reduce some of the issues with going back and forth when you talk about legal documentations and IRBs and so on, we used the FAIR model as a framework and created the first ever Chicagoland regional COVID-19 data comments. Next slide, please. So what are some of the major things that we achieved while doing this? The first thing that we had to do, and I think it was just alluded earlier, we had to go through the painful process of working with the major organizations that join us to do this, because each organization shared data differently and had different definitions for everything. So we went through the very painful, thoughtful, and very debated process of creating a data dictionary. That was key to some of the work that proceeded thereafter, specifically related to a paper that was issued from the data collected related to case fatality ratio. We also worked and partnered with SIU, who had developed a system to track mobility of COVID-19 cases. With Gen3 being the flexible and creating a user interface that allows you to bring in different systems, we were able to integrate what they brought in and then extend the use of the mobility tracking system they had started. So today we're working on log COVID-19 analysis and have developed a governance process to help drive some of the analysis forward. Ultimately, as of today, reaching 7 million subject level records from the members of the group to continue the ongoing research. I'm going to turn it over to Makisha Patel, who's a technical project manager and has led this effort. And as well, you'll hear from Urvi Shah, who is our software engineer that has done a lot of the configuration on this. Makisha.
Thank you, Paman. Hello, everyone. I'm Makisha Patel, Technical Project Manager at Open Commons Consortium. Next slide, please. Next, yeah. So we will walk through how OCC collaborates with various organizations and universities to collect and manage data. We'll cover the complete steps from contracts and legal documentation to the final submission of data to the PRC Data Commons. Next slide, please. Yep. So the first step involves contracts and legal agreements. This process involves signing agreements that are legally binding and compliant with data governance standards. These contracts define the legal parameters for data submission, ensuring compliance with all relevant regulations. And for making this process easy, we have defined all the agreements and contracts here. Can you please click on the link provided here? I just want to walk through the link. Anyone who's upright? Yeah. Thank you. So we have defined all the agreements and contracts here. So for by this, all the member organizations have easy access, and we have eliminated the emailing process. So that's how we have made the user-friendly this legal agreement procedure. Moving back to the slides, please. Sorry, can we see the slides? Thank you. So currently we have 4 member organizations that submits the data quarterly to us. That are Rush, North Shore, UIC, and UChicago. So the next step is IRB approval process. In the IRB approval process is mandatory for all participating organizations and university. This ensures that the data collection and submission process adhere to ethical guidelines. and RB approval must be obtained before any data fields are uploaded. So next slide, please. Moving on to the very crucial step. This is very crucial step of aligning the data to the data dictionary. This process minimizes discrepancies and enhances the data quality, ensuring that all the submitted data is standardized, making it easier to analyze and integrate. And the defined data dictionary for pandemic response commons can be viewed here. Like we have the defined data dictionary on the Chicagoland pandemic response common. The link is provided here. And currently on the Chicagoland COVID-19 data commons, we have 41 nodes and 1,245 properties. So we align all the data to the data dictionary before it's being uploaded to our data commons portal. So the next step is member onboarding to the PRC. In this step, OCC will create a project to host the data of a particular organization, and we provide the necessary access to the member organization to upload the data into the PRC data commons. So these are kind of a preliminary steps before moving on to the data submission process. Next step, next slide, please. Yep, and any question till now for any of the preliminary steps we have defined here before moving on to the data submission process? I think, okay. Urvi, over to you. Thank you.
I was talking on mute, I'm sorry. My name is Urvi Shade and I'm software engineer at Open Commons Consortium. Praman and Makisha are responsible to get the data to us and talk to different organizations and make sure everything is fine. And my job is to get all that data to be cleared out and put it into data commons for everybody to use. Next slide, please. So once the data has been collected or fetched, given to or fetched by Makisha, the next step is for me to do data pre-processing and validation, just to make sure that all the data is fine, is following all the guidelines that it used to, and what the data format is. So we do the validation for that data. We receive data in either structured or unstructured manner. So the structure manner, the data is basically given to all data commons nodes, and in unstructured, that can be supporting files like supplementary files or papers or something else. So depending on what kind of data we're getting, we validate them and put it into different procedure to be submitted into the data commons. Data modeling is basically we would be aligning that whatever data we receive to the data dictionary and make sure the model is working and compliant with the data commons. The stakeholder training is an optional step if the stakeholder have any members or any employee who are technically capable to do the data upload process by themselves. We provide that training as well, or OCC also provides the facility to upload the data on the organization's behalf. So we are really flexible in that way. The next step is basically to upload the data. We upload the data and into data commons into projects, and according to whatever has been decided between organization, the projects, the data end up into those particular projects. Once the data is uploaded into the projects, we do data visualization and utilization. So that enables data access for various analysis and visualization in Gen3 data commons. Is it okay if I can share my screen really fast?
Yeah, should work.
1 second, I should be here. Sorry. Thank you, everybody. Can you see my screen?
We see a waterfall, if that's what we're supposed to see.
Yeah, that's what I was aiming for. That's right. So in data utilization and visualization, the data is either submitted for researchers to do analysis, or we can do for multiple visualizations. So I'm going to take you guys to our current data commons, which is Chicagoland pandemic response commons, which Pavan was talking about in the start. So as you can see on the screen, the first visualization that we did in the initial days was to talk about the mobility of COVID-19. So you can see like multiple strains of COVID and how they have traveled across Chicagoland commons. And this is all put into Atlas. The next thing that we did was we put data in, we put publicly available data, which is the City of Chicago data set, into a different analytical dashboard to help researchers to understand and do research. And these all are interactive dashboards, and you can just at least do the basic visualizations. And this provides more information and more visual aspect of it. The third and the last thing that we're doing today is we're working with different organizations to get long COVID data, just to push our research further. And currently we have around 7 million records with ICD-10 codes, and we have worked with different organizations across Chicago, which Makisha was talking about, to get that clinical data on the same level. And currently we are getting more data, and we are working towards doing more research on this. But that's it from my end. I'm going to stop sharing. Any questions for any throughout the process or anything?
I think we made it on time. That's good here. Michael, back to you. Thank you, guys.
Thank you.
Thanks, Plum and Makisha and Urvi. Yes, and also thanks for being on time. So I'm going to now turn it over to Chris Meyer from the Center for Translational Data Science at the University of Chicago. Take it away, Chris.
Thanks, Michael. Yeah, I'm on Bob Grossman's team here at CTDS in the user solutions and scientific support team. And I'll talk about the Medical Imaging Data Resource Center with a focus on the work that the Gen3 team here at the center does. Next slide. Just a little background on MIDRC, which is the Imaging Data Commons we'll be talking about. So it was launched in 2020, specifically to address the COVID-19 pandemic. And its aim is to accelerate machine learning innovation by providing access to researchers to high quality curated medical imaging and associated clinical data. It's funded by the NIBIB and is hosted at University of Chicago and co-led by 3 radiology organizations, the American College of Radiology, the Radiological Society of North America, and the AAPM. Like I said before, most data are COVID-19 related, but MIDRC now is expanding to other diseases like cancer and long COVID. Next slide. MIDRC operates 4 Gen3 environments. 2 are production environments. One is the open access data commons at data.midric.org, and the other is controlled access at validate.midric.org. The open data are for training AI algorithms, and the controlled access, or also called the sequestered data, are for testing trained algorithms. And we tried to do to separate the data in a balanced way so that the 2 cohorts are demographically balanced. And we also have 2 staging environments. And the reason we have the staging environments is we ingest data into the staging environment first before publication so that we can do a thorough review of all the UI components and the data itself before we publish to production. Next slide. This is just an overview of MIDRC's ingestion process. And I won't dwell too long here, but basically, just to give you an idea of the cadence, we do try to publish a quote unquote release every month. And the release consists of new data, service, Gen3 service updates, as well as any configuration of the data portal UI. We do at Gen3, we do a couple different QCs. We do one immediately when we receive data, and again before we publish data. And in between those 2 QCs is all the data processing, which I'll go into more details later. But the point I want to make here is that for each of these steps, we have standard operating procedures that are well documented and lay out all the responsibilities of all the parties involved and how those processes go. And as much as we can, we try to script these processes in Python particularly using Jupyter Notebooks with documentation. And that's for the QC, all the data prep, and as well as the release itself. Next slide. In terms of how data gets to Midric, there are many contributing sites. These are medical centers that collect patient images and associated clinical data. And all of those contributing sites, the data from those sites flow into two primary data intake portals or data coordinating centers run by ACR and RSNA. Those are SEER, or the COVID Imaging Research Registry, and RSNA's RICORD, or the RSNA International COVID-19 Open Radiology Database. And the services ACR and RSNA provide Midric they collect the data from medical centers, they de-identify both the structured data from the EHR, also known as electronic health records, and the images themselves. This consists of, for example, date shifting any dates. We don't store actual dates. Removal of any PHI related to subjects like names and locations, etc. And for images, that includes facial blurring, skull stripping, removal of any burned in names or dates or anything like that from the images. And then finally, after data are de-identified and compiled into TSVs, these data coordinating centers provide the Gen3 team access to batches of data in order to ingest it into the Midric Commons. Next slide. Obviously, or at least apparently to anyone who works with Gen3, you need to have a data model for harmonization and building cohorts. So the purpose of the data model is primarily to support cohort building, not just to store the data. We index the data files and any clinical files, but we want to make those findable, and according to the FAIR principles, by creating a data model that supports user queries, common use cases. There is a working group in Midric called the Data Standards and Information Technology, or DSIT working group, that collaborates between the data coordinating centers, ACR and RSNA, as well as some representatives from the Gen3 team here at UChicago and at APM. And then, as I said, the data model is collaboratively created, and RSNA and ACR, as the data coordinating centers, extract the DICOM metadata from batches of images and organize it into submission TSVs that conform to this data model. And then similarly, associated clinical data is also extracted from EHR, de-identified, and organized into submission TSVs that conform to the data model. Next slide. This is just an overview of how data gets to the Gen3 team before it's ingested into Midric. So the contributing sites, these are medical centers, all contribute data to their chosen data coordinating center, either ACR or RSNA, who then de-identify batches of data. And what I mean when I say batch is often in science, you think of data sets. These are like discrete data sets that were created for a specific purpose. In Midric, a batch isn't necessarily, a quote unquote data set. Instead, these are just patients that have gone to the doctor for COVID. They've had imaging done and some clinical data has been collected. So there's no clear beginning and end date to the study. It's just an ongoing collection of data. So a batch is whenever we draw the line in the sand and say, okay, we're going to process this amount of data and send it over to Midric. And that consists of structured data and submission TSVs, image files, and then an image manifest that lists all the files that we should have. And then after that batch of data is transferred to the data coordinating center bucket, they'll notify the Gen3 team that then goes in and copies the data to Gen3 owned buckets. Next slide. Before we begin any processing of data, it's important, we've found, to perform what I call a pre-ingestion QC. And basically, this is just ensuring that the data are complete with respect to what they've told us they've given us. For example, if they say we've given you 1,000 cases with 10,000 images, we go in and make sure that those numbers align. We make sure the data are complete with respect to required fields in the data dictionary. And we give a report back on any optional fields, like we tell them, you haven't given us this field, or you only given us like 1% of images have this particular field, just so they know. And then we check TSV submission TSV formatting, like for example, the submitter IDs are all unique, the type is correct for the type of node, etc. And then if the data batch fails any checks, that allows the Gen3 team to, in a timely manner, notify the data contributor and request the batch be corrected and resubmitted. As opposed to in the past, before we had these checks in place, we would hold on to the data until we're ready to process it. And then, further down the line, we'll start to notice mistakes. And this just puts all those QC checks up front so that things go more smoothly. Next slide. In Midrick, because we're a data commons that is supporting AI algorithm training and testing, we split the data that comes in between the open and sequestered commons I mentioned before. We use a stratified sampling algorithm for this in order to create cohorts for testing and training that are as balanced as possible with respect to these attributes that are listed here on the left. Basically patient demographic attributes, as well as a small handful of imaging attributes like modality, body part examined, and then the study description. So yeah, this is sort of the first step in processing the data as we split it into these two different groups, open data and sequestered data, and those go into the two different environments. And I have links here to the algorithm itself, as well as the publication for it down there at the bottom. Next slide. Also worth mentioning that we have a image file packaging and indexing process. So when we first started Midrick, we found that indexing image instances led to slow download speeds and slower searches. And this is because some volumetric imaging modalities like CT and MRI, a single image, quote unquote, is like a three-dimensional stack of image slices. And this could be hundreds or even thousands of individual DICOM format image slices that all together form this three-dimensional single image. So in general, researchers don't want access to a single slice from the stack of images. They want the whole stack because they're all related. So we thought it would make things much more efficient if we packaged the instance files into imaging series level zip files, and those are indexed. And when a user does a search in the data portal and has selected, for example, some patients or some imaging studies that they'd like to download and analyze, they end up getting zip files instead of a giant list of instance files. Next slide. We also feature in Midrick a DICOM viewer. So in the Data Explorer, which many of you are probably familiar with, we have a button. And when you click the button, it will launch the OHIF DICOM viewer, which has been integrated into Gen3. In order for this to work, currently, we need to run in parallel an ORTHINC server, which organizes image instances into series and studies to make viewing easier. So we do duplicate the data in that ORTHINC server. Next slide. Finally, in order to complete submission of the data, once the image files are packaged and indexed, we join those image package or zip file GUIDs to the imaging series metadata TSVs, and we submit those via Sheepdog. And for our data submissions, we use the Gen3 SDK function, Gen3 submission submit file function. The submit file function, if you haven't been using it or aren't aware that this exists, in my opinion, is much preferred to using the UI for data submission, because It can do things like retry API requests on service failures, and it will actually subset the records that have failed away from the records that have succeeded, so that it makes retries easier. It also returns all the error messages for failed submissions to make troubleshooting easier. And you have all that information at your fingertips in the terminal where you're running this, instead of having to copy and paste out of a window in your browser. Next slide. Finally, there's a couple different things we do to calculate derived properties. The first one here is an example. So to capture certain use cases, we do calculations on the original data to create these so-called derived properties. So one example is shown here, which is the number of days from an imaging study to a negative or positive COVID test. This was one of the main use cases for researchers. They wanted to be able to say, give me all imaging studies that are, say, within 1 week window of a positive COVID test, and where so that they could consider that a COVID positive imaging exam versus a COVID negative imaging exam. So we run a Jupyter notebook that calculates these derived properties from the raw data, and prior to a data release, we submit those derived values to via Sheepdog to the database before they're ETL'd. Next slide. And then the other thing we do in terms of derived properties is we do something called LOINC mapping or LOINC harmonization. So another subcommittee of MIDRC, the Data Quality and Harmonization Group, has used the LOINC standard, which is a radiology standard, or I don't think it's just radiology. It's a healthcare standard that's used to that MIDRC uses to harmonize over 1,700 imaging study descriptions down to only 75. So if you can, so yeah, in the original data, imaging study descriptions can be just typed in by a technician who's running the imaging equipment. So you can imagine across hundreds of hospital sites, the technicians type in different strings for the same type of study. So LOINC is being leveraged in order to harmonize those study descriptions. And we use the study description, modality, contrast indicator, and body part examined, the LOINC values for those in order to harmonize the data. And this is all done like the derived properties prior to release via a Jupyter notebook. Next slide. And then finally, before we do a release, we run the ETL. And this is to get all the data out of Sheepdog into Elasticsearch indices, which Guppy can query quickly. And Guppy queries or the data in Elasticsearch is what the data exploration GUI runs off of. So this is sort of the last step before we consider the data release, the monthly data release complete. Next slide. And then finally, before we pull the trigger and do a release, which involves copying the databases from staging to production, we run through a pre-release QC checklist. And this is just a formalized SOP that we've written to make sure everything is good to go. Because if you don't have an SOP, people make mistakes and forget to do things. So it's just a checklist that we run through manually. As much of it as possible is scripted, but some of this stuff is just doing spot checks of UI components and file downloads, checking that all the dictionary versions match between the different environments, making sure software versions are correct, and all the counts of files and metadata are what we expect. Next slide. And then finally, at the end of the month, after we've done all our QC and we've gotten, a positive check on all the QC items, we copy the databases from staging to production, and that includes IndexD, the metadata service, and Sheepdog. We also copy any relevant data portal config changes from staging to production, which of course would involve taking a look at the GitOps JSON, the manifest, and the ETL mapping. And then finally, after the databases are copied, we run the ETL in production to update Elasticsearch indices, and then do one final click through of production to make sure everything looks right before we announce the release. And then we also publish monthly release notes. There on the right is an image of what they look like. Basically, we just list the new data that we've ingested, as well as any new services and portal config changes. Next slide. And this is the end of my talk. There's a ton of people that are involved in Midric. This is a very small subset of them, but I wanted to call out in particular the Gen3 folks here at the center who have made this work possible. Al Liu, our PM, and I also listed there 3 of the past PMs, the whole user services team, and then our tech leads from Gen3, as well as you can see there all the co-PIs. If you want to read more about it, there's a link to midric.org, and you can find and read about all the different groups that are involved in Midric. Thanks so much.
All right. Thanks a lot, Chris, for going through all the steps for Midric data submission. It's complex, but there's a lot of features and great things, and it's great to see all that laid out. So now we're going to transition to, I think, a very different model, as I understand it, from talking to the OHSU team in previous meetings. So I want to turn it over to Liam and Jordan to talk about their experiences with Gen3 data submission.
Hi, everyone. Quick introduction. I'm Jordan. I have a computational biologist background. So what I bring to the team is more of the perspective as the data submitter, as well as user experience. Later on, also talking will be Liam, who's one of our engineers. And along with us and the whole OHSU team listed on this slide here, we developed G3T. And as Michael has mentioned before, we're going to focus on the topic of user-driven submissions in this talk today. Next slide, please. For a little bit of context, this tool was initially developed for the global network ACE. And so for those that aren't too familiar, it's essentially an alliance that aims to detect cancer as well as characterize different components of it that's across the globe. And so what this brings to the table is the need for data sharing in a very specific and secure way, as well as the ability to design a platform that is usable for many different users with different experiences. So we want to cater towards those that have more of a wet lab background and maybe less computational background, as well as those that are entirely computational in nature and are very familiar with running commands. Next slide, please.
Hi, everyone. I'm Liam. I'm one of the software engineers working alongside Jordan in the LROT lab here at OHSU. And this is just an overview of our current Gen3 system for ACE, primarily over 3 different deployments with development, staging, and production. But the big idea is that we're supporting 6 different institutions listed on the left-hand side: Manchester, Cambridge, Stanford, OHSU, Cancer Research UK, and University of College London. And we've developed G3T to be able to provide for each of these institutions a way for them to manage their own data and upload it to the larger Gen3 system. And on the next slide, I think I'll pass it back to Jordan to give us an overview of the data stewardship model.
Yeah, absolutely. So essentially what you could think of it as the Gen3 requester is the one that actually implements the programs from user submissions. And then separately, we have a DAC from each institution that's able to control and manage each of these, the projects as well as the users. And so this separation allows for a little bit more security along with that. And if we go to the next slide, we'll show an example of how we actually implement this using G3T. So the process initially is, hey, a data submitter comes in and they want to create a new project. They can run this G3T init command to essentially generate a new one that is seen as more of a request. Next, it's passed off to the data steward from the internal team, who then can go ahead and approve individual requests. Finally, it's then passed to a system admin who is the one that actually creates the project. And at that point, data submitters, as well as users in general, can download, upload data to the specific project that we've just created. Next slide, please. And so I wanted to first start out with this example of a user who wants to upload their data using our G3T tooling. One thing I think I want you to notice about this is that G3T intentionally mimics a lot of Git, where we have things like git add, git commit, git push. All of those we intentionally try to implement in G3T with a very similar function because a lot of our users do have experience with Git, and it will allow for easier transition using our tool and better understanding of it as well. So in our first example here, we're going to first add a file to the system using G3T add, and there you can then include any file path or name, as well as some optional parameters and flags that are shown here. Next, they're going to run G3T meta init, and what this does is G3T automatically generates metadata for these users based upon any file or files that they've added in the previous command. Finally, they'll be able to run G3T commit, add a message, as well as G3T push, and actually push the data to our server. One thing that's also really great that they've implemented is the G3T status, because sometimes with larger files or a large queue, it can take a little bit longer, and a little bit longer is, we're still talking like less than a second. But either way, one thing that's great to see is they can see this current status of it to see if it's pending or if it's complete. Yes, and next slide, please. And so taking a step back, when the user adds the data using their G3T add command, what G3T will do is they'll automatically create this meta directory. And inside of that, it will be automatically populated with these NDJSON files that have to do with the particular file or files they've uploaded. A user can easily go ahead and view those directly wherever they are uploading, whether it's local or remote. Or alternatively, what we've also been able to implement is they can go to the data portal and see the same contents of that shown here. And they're able to, one benefit of this is that they're able to essentially filter based upon any of this information that they had from their files. So making it easier for users to quickly find their data or relevant data. Next slide, please. And so in the previous example, what I showed was a very simplified version where, hey, I have this data, these data, and I want to upload it. Now, as we all know, data is not necessarily as simple as that. And oftentimes it's very complicated in terms of its connections with other files and data sets in general, where they share multiple properties. So an example could be, maybe we have two separate files for an observation from a patient's visit with their physician. What we hope to be able to capture is this level of detail and as well as the complexity from the user's request. So next slide, please. So how do we do that? So essentially what we can do is a very similar pipeline as we previously saw. However, I want to direct your attention to the first line, which is G3T add. So again, this is where we would add the path to our file, but we also have optional flags such as patient or specimen size, and we support numerous different hashes that allow for us to tag that individual file with some sort of identifier. So in our case, you could think of it, in this case, we could think of it as maybe I have two files that refer to the same patient, and I want to manually pick my own patient ID that ties them together. The remaining steps all the way to pushing it to the servers remains the same. And next slide, please. And again, what we can see, looking inside the meta directory, we have a few extra files that were automatically generated, but this is based upon the tags that we applied in the last step. So if we, for instance, have uploaded the data and we want to go to the portal and say, look at one particular patient, any of the files, whether it's molecular files, clinical files, etc., relating to that patient, we can easily do that in a very quick and easy way through the portal because we support that sort of filtering. Next slide, please.
Great. And once a user has added a file to their project, what they'll see when they create the metadata is exactly the JSON record on the left, in this case, a patient record. And G3T is built around the FHIR data model. So every sort of metadata that you see here is going to be following those FAIR principles that were mentioned earlier. In this case, we see two IDs. One highlighted in yellow is the idempotent ID used in the Gen3 system. And the green one is the user submitted ID. And in this way, G3T connects both the Gen3 system ID with that provided by the user, ultimately to make everything more searchable and discoverable through the Gen3 system. And on the next slide, I believe we'll see an example of a spreadsheet. We've worked with some great data analysts here when we've started developing G3T. And we found that a lot of data is stored in spreadsheets or CSV files. And so one of our lead developer, Brian Walsh, crafted this command to allow users to transform their CSV data into the FHIR model. On the next slide, we'll see an example of this that follows the same principles as before with the simple any sort of file, only this time we'll be using a G3T plugin as a way to transform those mappings between CSV into FHIR and ultimately into our Gen3 ACE comments. And so in this case, we'll see the exact same G3T add. There's the G3T plugin with G3T ETL transform command. And finally, that same commit and push that we've expected to use. And on the next slide, we'll see that same metadata be created in the meta directory, and then the same files on the right, in this case, the patient records, be reflected in the browser. Next slide, please. And I think we'll see our next steps for what we expect G3 to look like in the near future. This is definitely built with a community of Gen3 in mind. So we'd love any sort of suggestions and recommendations on your own use case. One of the big asks from our data analyst was to be able to upload multiple files in parallel rather than sequentially. And we're also working on making G3T as gradual as a road as a ramp for analysts to be able to use. So that just means expanding documentation, adding lessons and tutorials, and gradually increasing G3T commands and subcommands. Finally, we were hoping to hear more about the different ways people are uploading their own G3 data or Gen3 data. And it's been great to hear all the talks so far. Oh, and a big shout out to Michael and his team, Craig, and everyone Bedford for their work on the front-end framework. We're hoping to continue that integration with G3T with the front-end framework in Gen3 moving ahead. And I think, oh, in the next slide, I'll go ahead and paste the GitHub links that for Gen3 client or Gen3 util and G3T ETL. It's hosted in a public repo. There's a contributor guide. We'd love to see as many issues or pull requests as possible, but feel free to check it out. And yeah, we'd be happy to help take a look and see what we can do to help. And I think that brings us to the end. Thank you very much.
Great. Thanks, Liam and Jordan. And I definitely can take no credit for the front-end framework since that is all the Craig and his front-end engineers. But it is good to work with you guys on that project. So I think rather than take questions now, we'll just move on, although I have some questions for that and maybe some others do too. But we're going to move on to Josh Harris, who's a research data manager at the Australian Biocommons. I see a few Joshua Harrises. I'm assuming one of them is our speaker.
Yes. Is it okay if I share my screen? I just made a few tiny edits to the slides.
Sure.
Cool. Okay, can everyone see this okay?
Yes.
Right, cool. Yeah, so my name is Josh Harris. I'm a research data manager at Australian Biocommons. Firstly, here in Australia, I'd like to show my respect and acknowledge the traditional custodians of the land. These people were here well before us and were the original scholars and scientists of the land. Also acknowledge elders past and present in which this meeting takes place. So at Australian Biocommons, just a sort of quick rough outline, Australian Biocommons exist to support leadership, provide data infrastructure and analytics services to the bioscience and bioinformatic communities, as well as providing training and support. Whoops, sorry. And here at Biocommons, one of the main projects that we're working on with Gen3 is Australian Cardiovascular Disease Data Commons. It's very much still in development at the moment, but this data commons is planning to host around about 18 large cardiovascular cohorts from the country, and we'll be hosting quite an array of multi-omic and clinical data ranging from genomic to lipidomic, metabolomic, and some imaging data. So just want to give a very quick introduction to data modeling, and data modeling starts at the conceptual phase where we draw these conceptual entity relationship graphs, and this is where you map out how different tables or fields actually link to one another. Sorry again. And we can actually see some representation of this conceptual entity relationship graph in Gen3 when we look at the graph view of the data model. And I just want to define some of the terms that I'm going to be using in this presentation. You can see there I've put an arrow to one of the graph nodes, which in this presentation, for the sake of consistency, we'll refer it to as a data object, even though a data object could be many things. And then the links between these nodes or data objects are the links. And then when you actually click into some of these nodes, you get a bit more information. So you have the data type, whether it be a string or Boolean or integer. You have the enums, which are the categories of the data type. And then you also have the properties within that data object. So typically data modeling follows these steps where you start with your conceptual graph, ER graph, and then you go to a JSON schema, which is more computer readable, and then that can be loaded into Gen3 as a data model. However, this step between conceptual ER graph and JSON schema is something that is actually quite a a complex process in itself. And there's multiple ways about doing it, and that's what I'm talking to you guys about today, how we actually go about doing that in Gen3. So yeah, I'd sort of want to give my thoughts and experiences of data modeling in Gen3. And I should preface this is coming from a former bioinformatician and a beginner to Gen3 and a beginner data modeler. So the first way is actually reusing data objects from other Gen3 dictionaries. And there are some repositories around where they have their data objects or data nodes that are already on Git that are Gen3 compatible. And you can see some of these objects here, like align reads, and that will capture all the properties typically that you'd want to capture in a line read. So having these already online is quite useful, and having them separated as YAML files is also quite useful. And we've actually played around with just some basic scripts to pull in these YAML files into our folder of data objects and YAMLs and then recompile them into a JSON schema. And what we've found is that this actually does work in some instances, but then there are other instances where some of these data objects or YAML files have terms and definitions that run quite deep and have quite deep linkages with other the definition and YAML definition and terms YAMLs in the data model. So it is possible to do this. You'll just have to have a lot more robust reference resolution to do it. But that is one option for helping design your data model and to utilize previous work. And then the next is utilizing common data models. So in our field, in the health research field, there's a variety of common data models out there. These models are actually extremely powerful if you understand them well and you know how to use them and implement them. And they can definitely promote a lot of interoperability between systems and promote ease of use. However, the main limitation, and within the context of our project, where we have a very small technical team, is that jumping into something like Fire is really very much jumping yourself into the deep end, especially for a beginner data modeler. And so and what we've also found is that these data models aren't inherently compatible with Gen3, and you actually need some sort of ETL process to be able to convert the Fire ontology into the JSON schema format that's that Gen3 can read. And luckily there are some tools out there that have already done this, although it takes domain experts to do them. I think PBF Fire is one that's been used to convert Fire into a Gen3 JSON schema. But what we've found within our team at the end of the day is that even though you have all of this extensive ontology, there's still going to be an element at the very bottom of the tree of coding how you want to code your clinical your multi-omic variables, what extra data you want to encode and how you want to encode it. And sure, you can definitely get a can't remember the term, but there's an extension for Fire that you can implement. But like I said, that starts to circle back to the realm of requiring training and expertise in that to begin with. So the other way, which we have sort of leaned towards at this stage in the project, while we still have a small team and we're prototyping this, is building our own custom data model. And this has provided us with the best amount of efficiency. So it's given us the best balance of speed and efficiency for data modeling. And as I'll explain a little bit later, this works quite well in our data model development pipeline, which is actually tailored for speed and flexibility, so that we can actually keep iterating on this. And as the project grows and we have a lot more domain experts that can actually help us with the data model, then we actually have the framework and tools to improve on it quite rapidly. So just to finish off, there's I guess there is a need for some sort of entry-level data modeling tools for Gen3 just to try and bridge this sort of gap in domain and expertise, especially if you have research teams coming from a bioinformatic or research background that are not typically data modelers or software developers by trade. So here's a very brief diagram of our data modeling process, and we actually built a lot of the tooling to do our data modeling in Google Sheets. which provides an interface for us to do our modeling. And then that can be pulled in and then converted to our YAMLs. And then that is compiled into a bundled JSON schema. From that JSON schema, we can generate some synthetic data for that schema, which is quite important in terms of actually testing the data model and seeing if it actually gives us what we want to use on Gen3 in the front end. We can also do local visualization of that bundled JSON schema so that we can actually see what the data model looks like in almost real time. And then the cycle can reiterate, and we can actually see, oh, you know, what are some things that we want to do that we can't in the data model? Let's go back to the Google Sheet and let's do the cycle again. So our team and some of the previous staff in our team have developed this open source project called Gen3 Schema Dev. And this repository provides some tooling to actually do a lot of the schema development that I just mentioned. And the first thing it does is it actually pulls in data from 4 main Google Sheets: objects, link, property, and enum definitions. So I'll just quickly go through all of these. So the first one is actually defining your object nodes, and this is where you define those major points in the graph model. And then in the next tab, you define what are the links between the object nodes, the multiplicity. You define what back references you want to call them. Next, within each data object node, then you define the properties. And then we also have fields here where you can define, you know, regex patterns. You can define also term references for things that you want to put in consistently over a lot of properties. And then finally, you have your enums. So you can define an enum category along with all of its different values here. So within Gen3 Schema Dev, we have a script called sheet2YAML, and that just reads the Google Sheets, converts them to YAML. We've also built in some tooling into the Gen3 Schema library that concurrently downloads the Google Sheets, both as a CSV and XLSX, just so that you have a snapshot of what the Google Sheet looked like in that point of time. And then we utilize G3PO for compiling YAMLs into the JSON schema. The next step is to do the graph validation, and this is using UCCDIS data simulator within the UMCCR dictionary repository. And then once we've validated that the links you know, make some logical sense, it's really nice to be able to visualize the dictionary locally. And then we can just explore it as it would look in Gen3 without actually having to do any significant local deployment. And the good thing about this is it's interactive, and you can go and actually have a look at what you've done. And to get to this point from a Google Sheet to actually seeing something like this only takes about 3 seconds with running a Jupyter notebook. So it's been quite good and rapid for us prototyping and designing a data dictionary. The next thing we typically do is we use a data simulator to actually make some simulated data. And then after using the data simulator, we also have another data simulation layer packaged in a script called plausible data generation. And once again, this reads information from a Google Sheet, which could just be another tab in your own Google Sheet. And this will define what are the range of values that you actually want to simulate in your data. And so we have mean, standard deviation, the data type, the property. And then also we have some provenance here, so we can actually see where did you get those values from, so that you know that you're simulating data based off some sort of some sort of academic publication. So once we have the data model and we're happy with it and we've generated some synthetic data, the question comes to how do we actually manage this data model? How do we manage the synthetic data that's specific for that data model? And we've decided to opt in for packaging these into its own repo. This is a project-specific repo, so we've just called it AC/DC schema dev. You can see that we've got Gen3 schema dev here as a submodule within our repo. So all of the tools are within those repositories. But then we do have some Python notebook, sorry, not Python, some Jupyter notebooks down here that allow us to manage a lot of our processes in sort of a stepwise way where we have a little bit of control. And then once we actually have all of the dictionary generated, all the intermediary files, and once we actually have the synthetic data, they are all put into this output folder. And the entire project is just packaged into a Git release. And so we can actually, we can freeze that in time and say, well, this is our release. And if we want to load version 0.1.1 of the dictionary, then we know what version of synthetic data to load with it as well. And so this has been working quite well for us to do a lot of development and testing. And then so lastly, just some advantages and limitations to our methods. So the main advantage, as I've sort of alluded to before, is that it's really easy to use. There's a low barrier entry. When you do your data modeling, you're just looking at the parts that you're really focused on in the Excel spreadsheet. If you're not used to seeing a JSON schema, it's not as overwhelming. And it's actually quite rapid to do. So you can actually, even if you do want to take this to the next level at the very starting point, you can actually sculpt out a lot of your data model quite quickly and get it to a JSON schema. And then if you want to start doing some more advanced stuff like implementing some other standards in that from the JSON schema, you can. So this tool actually helps you, do a lot of that initial prototyping and bulk work. But the main limitation of this is that it's not reverse compatible. So going from a JSON schema to a Google Sheet, we haven't actually coded that yet. Ideally, if you could, because I know there's a lot of tools out there to convert a common data model ontology to a JSON schema, and that's great. That means you have to keep working in JSON schemas if you want to add to it. But it'd be even greater if you can convert that to a Google Sheet and just have something like go down to the observations plane and the fire model and then add in what you want and then go back and forth. The other thing is that, if you want to incorporate other Gen3 data object nodes, that needs to be inserted into the JSON schema after you compile the YAMLs. So that's also another limitation. And then in terms of future work, we're thinking of hopefully packaging this workflow and the tools into a more generic open source project and provide a bit more documentation. As I said, reverse engineering the schema back to the Google Sheet, and then finalizing some tools for Gen3 data model node / object ingestion. We've sort of just played around with and tested it, but I'm sure that you can actually make it a lot more robust by doing a lot more checks and doing a lot more stringent reference resolution. And yeah, that brings me to a close. So finally, I just want to acknowledge our funders, Bioplatforms Australia and the Medical Research Fund of Australia. Cool.
Great. Thanks. Thanks so much, Josh. Great to hear your experiences and approach to this. Okay, so we're almost at time. So I would say we have time for just a couple questions if people have some. Please feel free to unmute or type your question. Okay, I will ask a quick question then. I wanted to circle back to, I think, our first talk from Claire and Nat. I'm curious about your use of Globus and how you link, how you kind of make cohorts or search and then link to the actual files. What does that process look like? I don't, maybe you said it and I missed it. I just didn't follow that quite.
No, I think we probably intentionally didn't mention it. So you can search and through all the metadata, but and I guess we give file metadata within Gen3. So you kind of can see what files are available and what formats, etc. But we don't actually link directly to Globus. So once you've applied for access and if that's granted, then we will manually give you access to the file set that you've applied for or been approved for access. So it's a two-step mechanism, if that makes sense. So it doesn't quite link seamlessly. Something we will look at improving in the future and possibly bringing data files into Gen3. Now we're a bit more familiar with having our Gen3 up on OpenStack, but it's in the backlog, as it were. It's not going to be quick, I don't think, to change.
Okay, cool. Just curious. It seems to work for you guys, so I was just curious how it worked out. Anybody else want to ask another question? I think we have time for one more question. Okay. Well, if not, since we're at time, I just want to thank all the speakers. It's super valuable hearing everybody's approaches to data submission. I think we're all doing this, as I said, in different ways, and we can all learn from each other on how we're doing it. So I'd encourage everybody to, take this conversation if you have other questions or thoughts to the Gen3 community Slack page and continue discussing this. So thanks again, everybody. See you at the next forum.